Hey guys, and welcome back to another YouTube video. I haven't uploaded for quite a while right now, but I'm back. The reason for this was just because one, I was pretty busy with school stuff, and the other reason was that I was working on a very well prepared video, and I really wanted to make this video for a long time, and I finally got around to doing that because I myself got to a point in with my learning wherein I was confident enough to make this video and not really mess up a lot of information. There's obviously still going to be a chance that I might mess something up, but the chances now are pretty less. So this video is gonna be the start of a pretty cool series where we are really gonna see what a neural network is right from the start. We're also gonna be coding out neural networks, and this is gonna be something. This won't be a zero to hero. This will be wherein if you have a little bit of understanding of what neural networks are, you can jump in and you can really kind of understand how to create more complex neural networks, how to understand neural network architecture. So for example, if I were to say uh, how does how exactly does, I would say, any something like AlexNet or something like LeNet work, and you will be able to figure that stuff out. More than that, you will also know how to work with ResNets. We will also be looking at stuff like residual neural networks. I'm not sorry, not residual. Sorry, RNNs, recurrent neural networks, and we're also going to be looking at GANs and everything. So this is going to be the start, and I have actually started to create a not a book, but this is going to be somewhat of a reference book. This basically deals with the basics, like this is gonna have like all of the things that you probably might want to look up sometime, and this is just gonna have notes on that. So for example, once I sh- you know upload this video, I'll also make this available on GitHub. And so what you will be able to do is you will be able to basically uh, read through this after you've seen the video. So even after you've seen the video and you're trying to apply something to your project, however you can't, then you can just go and open this PDF up and see how to do it. So as you can see, I have spent a lot of time. You can see that it is really kind of formatted very well, and so I have spent a lot of time trying to make sure that everything is looks good, and the information that I'm providing is correct. So that was kind of like a long intro, but let's jump right into it. So in today's video, we are going to be talking about optimization, and we are going to be talking about various optimization techniques. And so as you can see, there are multiple optimization techniques over here. We have gradient descent, momentum, Nestro's accelerated gradient, Adagrad, RMS prop, Adam, and Nadam. Now, out of these, like these two are very similar, and these two are very similar, and so we might not spend a lot of time. The first thing that I really want to teach you is gradient descent, because I'm pretty sure you have probably heard the name gradient descent why in some form when if you are trying to deal with neural nets and machine learning. So as you can see, there are a bunch of mathematical equations here, and I would recommend you know your multivariable calculus before you watch this video. So just heads up. So what is gradient descent? Gradient descent is one of the most popular neural network optimization techniques. It was one of the first, I'm pretty sure, but I don't really know the history of neural networks. So yeah, it involves computing the negative gradient of the model weights and then modifying the weights in that respect so as to converge to a local minimum or a global minimum. I know this sounds a little technical and more like your Wikipedia definition, and so I'm gonna show it to you a bit better so you can kind of understand what exactly is it that I'm trying to say. So I want you to imagine some sort of a graph. Just imagine it to be something like this, and this is just gonna be your loss. Now you wanna reduce this loss, right? That's gonna be the entire purpose of your model, to reduce the loss function. And so you probably wanna convert somewhere over here. Now, ideally, you might want to converge here, but this stuff isn't always possible. A lot of the times, it's just not possible to converge to a global minimum just because your initialization were very far off, and so it would become basically impossible to converge to a global minimum, and you might just have to run the model again. But that besides the point. So we want to converge to a minimum, and I'm pretty sure the people who have taken calculus or they know calculus, they obviously know that we can actually differentiate a function to calculate its minimum. We all know that. So if we have any function, we can just differentiate it, then we can get the minimum of the function. But usually we don't do that with neural networks. The reason is that a lot of the times the functions that we're going to be looking at will be very big functions, and it would just not be an ideal if you know the big O complex, the big O notation in computers, you know that we measure the time complexity using the big O notation, and usually it goes to something like O n cubed and something like this. So the time complexity is going to be very much. So what's going to end up happening is when you actually try to execute that, it will take a lot of time to do that, and it just won't be that great. And so also because you're not going to be dealing with just two-dimensional functions, sometimes you're going to be dealing with like 15-dimensional functions, 20-dimensional functions, depends. So in such cases, obviously just doing like d by d whatever is not going to help you out that much. I'm not saying that in some very simple scenario you can do that, but in 99.99% of the scenarios you just can't. So what we instead do is we make use of this equation right here. Now let me explain to you what this equation really is. And before I do, I'm just gonna polish up the idea of what a gradient is. So I'm pretty sure if you have taken multivariable calculus, you have seen this notation show up quite a bit. This little upward down triangle. So but I'm still gonna kind of show it to you because yeah, just for the people who don't know. So let's say I have a function. Now when you have said f of x y is equal to x squared and y squared, note that f depends on x and y both. So we know that this is like a multi-variable function. Now, uh, let's now I would just want you to forget this thing for a moment, and if we were to graph this now, this might I think look something like a two-dimensional parabola, something like that. I don't know, but it should look something like a parabola. And if you guys really and just so that I can kind of show it to you, you can just go ahead and graph this out. You will see it looks like a parabola in 3 dimensions. So yeah, that's besides the point. So we know that this is the case. Now if we are standing at a point and we need to figure out the direction of the steepest ascent, the way we do that is we do the grad of fxy. So that means that we are calculating the gradient or the vector that points in the direction of the steepest ascent. The way we calculate that steepest ascent, you might ask? Well, that's actually a very simple thing. You just create a vector of the partial derivatives of each of these. So you will do del f by del x and del f by del y. And that's all you really need to do. And that should give you del nabla f grad f x y. So now we know that the gradient. Now in this case, obviously it's very simple computation. It's just going to be 2x to y. But in some cases, the computation will be a little difficult. I'm not going to go over how to compute it. It's pretty basic stuff. So I'm not going to go over that. But yeah. Now in this case, we don't want to calculate the direction of the steepest ascent. We want to calculate the direction of the steepest descent. So, very genius technique. You just do a negative gradient or whatever it is. In this case, you will see we have a negative grad j theta. So that's just notation. You could just say f theta or fx. It's just notation. So alright, so now we have derived this part of our equation, but we still do have this little eta symbol. If you don't know eta, it's a Greek symbol. Yeah. pretty cool. So we should love that eta symbol. Now the eta symbol really is just the step size or the learning rate. What does learning rate mean? Why am I just throwing words at you? Well, let me explain to you that also. So really what the learning rate is, it is the size of the vector with which we actually fall down and converts to a minimum. Now, so this is just really gonna be like, imagine if you are on the fourth floor of the building and you have to get to the third floor of the building. Now, imagine if there were just no steps. Now you probably might jump and you probably might enjoy yourself, and it's just not gonna be that great, right? So you're gonna be like, no, I don't want to jump. Now, there's just one condition to everything, that when you're actually going down your steps, you actually have to pause for 1 second every time you go down a step, and you can't skip steps. So that's your conditions. So it'll be like, all right, well, okay, I understand. Now imagine if there was just one step. Now it wouldn't take you that much of time, but there's still a possibility that you might get injured. And you know what? Let's just imagine that these two floors span a height of 100 meters. Now imagine if there were 3 steps, 4 steps, 5 steps. Now imagine if there were, now probably if there were like 100 steps, the time would be sufficient and you might not get injured and it will be very good. But now imagine there were 1,000 steps or 10,000 steps. What's gonna happen is, since you have to pause for every second or every minute, it's gonna take you a lot of time. And let's say at one point you will just give up and you'll be like, you know what, screw it, and you will never reach the end of the staircase. And that's exactly the learning rate. It is the step size. It's the size of the step to converge to a minimum. And basically, so a lot of people I've heard, they are going to be like, you got to choose a small learning rate. No, like, yeah, you should choose a small learning rate, but that doesn't mean like you just do like 1 e to the negative 10. You don't do something like that. You gotta think. Usually we do like 0.01, 0.001, something like that. So yeah, that's the learning rate. So now we have derived this part of the equation. We have derived this much. In this case, this is just going to be a cost function j applied to your theta, which is going to be your weights. So now we have derived this much of the equation. As you can see, I'm actually making you guys derive this equation, so you really understand the crux. Now, since I told you, we have to subtract this from our initial weights. So we have our theta, which is going to be our initial weights, and when we do that, we get a new theta, and there we go. That's our equation. So another thing would be a theta nu is equal to an old theta minus eta grad j theta, and that right there, my friends, is gradient descent. Technically not gradient descent, it's batch gradient descent, because you're applying it to the entire sample size or the entire data set, which isn't a great idea. Really, just don't do batch gradient descent. Don't apply gradient descent to your entire thing. It's a very bad thing, because time increases a lot. It takes a lot of time. So here I've just calculated grad of MSc theta, and I've just shown you what it is how it is that it works. I also said this is batch gradient descent, where the batch size is the complete data set. Thus naturally it gets very slow. Now, however, you can see that gradient descent isn't the most quick method. I mean, yeah, it's good, but it's also pretty slow. So we gotta figure out a better way to do it. Now, this is where we have momentum. So I'm sure you probably know momentum from physics, and you will see how it kind of now so like you can see that momentum is something that we have already used in physics. It's something that we use to describe motion and stuff. So in the momentum optimization technique is really just something that we can use to speed up, and we can also use it to better gradient descent in a way. So normally gradient descent works, we know that, calculating negative gradient of cost function, subtracting it from the parameter vector, However, in momentum, we add an extra term beta to the parameter vector or the model weights, which acts as the momentum. Momentum cares a lot about the previous gradient. So, momentum values range from 0 to 1. Typically, it's 0.9. 1 means very little friction, and so there will be a lot of speed ups, but it will also lead to overshooting. 0 means you just don't want to go 0. It will basically just not cause your model to go further. The way momentum works is literally just by the gradient descent technique, except for the fact that we just represent it into equations. Over here, we just add a beta term to the previous like output, whatever you wanna call it. M is the output, and then you just add it to theta. Now you will see that this way, since we have a beta term right beside the M,